All right. Hey, check this out. In this video, I'm going to do a statics example with a beam with a hinge on it and and I'm just going to show you how to handle that hinge here. So in this problem here, I got a beam that's fixed at point A right here. It's got a concentrated load at B, and then it's got this hinge here. This hinge, little round ball right there is a hinge at C, and and then this roller support at D. And the hinge is a moment release. So what that means is that the moment at point C, if I were to make a cut at this point, the internal moment there is zero. Okay, and that helps this structure as a whole to become what's called statically determinate. Anyway, but here I'm gonna show you how to handle this. Okay, because you're gonna draw this and you're gonna say, okay, well, I got to find my reactions in this problem at A and D, and I got here, I'm gonna say, okay, I've got a AY, a horizontal AX, and at a fixed support, I've got also a moment at point A. So I've got these three reactions at a fixed support in 2D, and then here at point D, where I have a roller, I have a DY. Okay, and using three equations and three unknowns on your three equations, some of the forces in the X, some of the forces in Y, and some of your moments on this whole structure, you can't solve for it. Okay, so what the thing you want to do is, after you draw out these, you draw your free body diagram, so draw FBD, and then you want to separate at the hinge, at hinge. All right, we're going to separate at the hinge, and we're going to make two separate drawings. So here I've got this, here this A. See if I can draw this pretty good. Here at point C, up to point C here, and for this beam I've got 5 kilonewtons going on here. I separated at the hinge. I've got the AY, the AX, and the MA. Okay, so I've got here, and then here I'm going to separate. Oops, let's get that back to black. So here I've got I've got this beam over here, this part of the beam, part CD, and here I've got a roller and a distributed load. Okay, and whenever you have a hinge, what it means is, you know how sometimes you take if we take a beam right here, so let's say we have a beam here, you make a cut and you draw the internal loading in the positive sense. So this is one of the first things you learned about positive sign convention, okay? And it's important that whenever you make a cut, you draw in terms of positive sign convention. So when you make a cut and you look at the left side of the cut, positive shear is down, positive axial force in the member is away from the cut or perpendicular to cut, that normal force, and the moment here causes compression at the top. This is positive sign convention for the cut on the left. And then same thing here, if you make the cut and then you look at so if you make this cut and you go look at the right, then the positive sign convention is axial force N pointing away from the cut, okay, causing tension, shear pointing upwards V, and M compression at the top. Okay, so in most textbooks in the United States that teach like statics and mechanics, this is our basic internal positive sign convention. You want to make sure. Now, what the hinge is it's when I draw this right here, it's a cut here, right? But the moment, these moments right here are zero. So at the cut here, and I'm going to label N and V, instead of labeling them N and V at this cut at the hinge, I'm going to call it right here. I have the right side of the cut over here. I'm going to have this shear CY, and I'm going to call the axial CX, okay? And then if I look at the left side of the cut, or the equal and opposite, I would have this CX and CY, okay? And because of the hinge here, it's a moment release, I have no moments on no internal moments, okay? And what happens is, like, we label these CY, CX, and people get so used to seeing these as external reactions, you get all confused. But for really all intents and purposes, these are internal forces that are going on inside the hinge. Okay, this CY and CX are internal forces at the hinge. So they really just correspond to a normal force and a shear force at C. All right. And then here I have this dy here. But what it does when I separate at the hinge here, going back to the point, what it does when I separate at the hinge here is that it leaves me with a free body diagram here where I can apply three equations, three unknowns. Okay, and I know that this is 1 kilonewton per meter right here. And if I some of the forces in this part right here, if I apply some of the forces in the x, that tells me here. This is positive. This it tells me that Cx is 0, obviously. Okay, and then I could sum moments about C equal to 0 at this point. I go like this right here. That'll tell me dy times 6 meters. This was 6 meters, and this was 10 or 5 and 5 meters. Okay, dy times 6 meters. Okay, so right here, boom, minus 1 kilonewton per meter times 6 meters times, the resultant is over here, so this distance to the resultant is 3 meters, okay, right here. So the resultant is 6 kilonewtons times 3 meters equals 0, and that tells me that dy equals 3 kilonewtons, okay? And then from some of the forces in the y, or some of the forces in the y equal to 0, positive this way, dy plus cy equals, or cy, how about we just put it like this, minus 6 kilonewtons equals 0. That would make cy also equal to 3 kilonewtons, okay? Another thing to look at here is that the loading is symmetric, the structure here is symmetric, so I know dy and cy are going to be equal to each other, and they're going to be half of this resultant right here, this resultant, which was 6 kilonewtons. Okay, so 3 and 3. All right. So I know that, okay? So I know Cx, I know Cy now. Now I can apply this over here, okay? So I don't mess around with the directions of the arrows or anything, but I do know that Cx is equal to 3 kilonewtons. I know Cy is equal to, ooh, whoa. Cx equals 0. Cy equals 3 kilonewtons, right? And now I can go to this free body diagram right here and apply 3 equations and 3 unknowns. So here I apply some of the forces in the x equal to 0. This is trivial, and that tells me that ax equals 0. Then I can apply some of the forces in the y. Some of the forces in the y equal to 0. I'll say the vertical upwards is positive. That would tell me that ay plus cy minus 5 kilonewtons equals 0. Aha, I almost made a mistake here. This right here is minus cy right here, okay? And here, this would tell me that ay minus 3 kilonewtons minus 5 kilonewtons equals 0. That tells me that ay equals 8 kilonewtons, okay? 8 kilonewtons right here. And if I want to find m sub a, the moment at a, I would take the sum of moments at a, about point A, right here, and I'll call this counterclockwise is positive equal to 0, and that would tell me that ma, let's see, minus 5 kilonewtons times 5 meters, so the moment induced by that 5 kilonewtons, minus the moment induced by Cy times 10 meters. And this number is 3 kilonewtons. And this equals 0. Okay, so I think I have all the moments. And this tells me that MA, it will be 25 plus 30 is going to be 55 kilonewton meters. Okay, and this positive number indicates to me that my direction that I guessed is correct. All right, and so finally, all this together, I could redraw the entire structure right here. I redraw the entire structure like this, and I know I forgot the hinge here, but I have this hinge, and I have this right here, and I would have, and then if I want to get ready to draw the shear moment diagram, I would go here, 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 1 kilonewton per meter. I would probably set it up like this, just to make sure AY would be 8 kilonewtons, dy is 3 kilonewtons right here. This moment about A was 55 kilonewton meters. And this is how I would set it up to draw my shear. Don't forget this 5 kilonewtons here. And my lengths, okay, right here. This would be 6 meters. These are 5 and 5. Oops. 5 and 5 meters right here. And this is how I would set it up to draw my shear and moment diagrams, which I'll do in the next video. All right, see you later.